All right, I'm going to try to make some videos on lab skills, and we're going to start with uncertainty and measurements. So the first question is, what numbers need an uncertainty? When do we need to have uncertainty for numbers? And it's basically going to happen anytime we measure something or that somebody's reporting a measured value. So what this doesn't mean is when we're counting. So if I want to know how many chess pieces are on a chessboard, or how many students are in a room, or how many stuffed animals my daughter has, I can just count those and I get an exact answer, right? If there are 24 students in the room, there are exactly 24 students, not 24.06 students. So anything you can count would be an exact number. There are some other exact numbers like pi. Pi is an exact number. 3/5 is an exact number. So those kinds of things don't have uncertainty. But if we are measuring an object's mass, or we're measuring a force, or we're measuring a voltage, or we're measuring a charge, those kinds of numbers we can't find exactly. Every measurement we make is going to have some uncertainty. So it is important, it is maybe just as important to know the uncertainty in our measurements as it is to know the actual value of a measurement. So for an example, if I tell you that I'm 5'9", 5 foot 9 inches, that information isn't very useful unless you know also what the uncertainty is in that measurement, in that value. So as physics students, you're going to be expected to report the uncertainty in the measurements you make. So I want to talk about some different scenarios. So the first scenario I want to talk about, and now we're moving on to point 2 in this video. The first scenario I want to talk about is when we have I want to imagine that we had a perfect digital instrument. You could imagine a stopwatch, or a scale, or a multimeter. We'll be using those in class in Physics 2. They measure voltage and current, among other things. But the thing that all of these instruments have in common is that they have a display that has numbers. So it could read something like 12.476. And if this was a stopwatch, that might be 12.476 seconds. If this was a scale, that could be 12.476 kilograms. And if this was a multimeter, that could be 12.476 volts. But let's assume it's a scale for a minute. And let's assume that the scale is perfect. Like it has absolutely no flaws. It can measure the mass of an object exactly perfectly. Now, in the real world, that's not true, but let's pretend it is. Let's pretend we have a perfect scale, and it told us that the mass of an object was 12.476 kilograms. Does that mean that the object has exactly 12.476 kilograms? Like 0.0000000 kilograms. Does it mean that it's exactly 12.476 kilograms? Well, no, of course not. Because the scale only has those 5 digits. It only has 3 digits after the decimal point. So even if the scale knows exactly what the object's mass is, it can't tell us exactly what the object's mass is. So if the object's mass was 12.4758321 kilograms, what the scale would have to do is say, well, that is between 12.475 and 12.476, but it is closer to 12.476. So as a perfect scale, I'm going to report 12.476. On the other hand, if the actual real perfect mass was 12.4 0.4762119 kilograms. Again, the scale, it knows what the perfect mass is, and it's somewhere between 12.476 and 12.477, but it's closer to 12.476, so it's going to report 12.476. And I want you, if you're willing, to pause the video and think, like, what's the biggest mass the object could possibly have, and the scale would still report 12.476? What's the smallest mass it could possibly have, and the scale would still report 12.476? Okay. You want to think about it for a second, maybe press pause. Okay, so let me tell you what I think. I think that if the biggest that the mass could actually be is 12.476499999 kilograms, because if it was any higher than that, it would be closer to 12.477, and the scale would read 12.477. That's the biggest it could possibly be. The smallest it could possibly be is 12.475000000. If it was any smaller than that, it would read 12.47. I did write that incorrectly. My mistake. 12.47. Five zero 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 zero, and right, this is just a little bit closer to 4.576 than it is to 4.575. If it was just a tiny bit smaller, it would round down to 4.575. If it's just a tiny bit bigger than that, it would round up to 4.576. So what do we say now? For simplicity, let's get rid of those extra zeros, and for simplicity, let's round 49999 up to 5. And what we're saying is that it could be anywhere between 12.4755 and 12.4765. And that means it could be 12.476 plus or minus 0.0005. Now, how do I know that? Because if I add 0.0005 to 476, I get this number. And if I subtract 0.0005 from 0.476, I get that number. And so the range of possible values from this perfect scale goes anywhere from 12.476 plus or minus 0.005 kilograms. So if we had a perfect digital instrument, like a scale or a clock or a multimeter, if we had a perfect digital instrument, the information that the instrument gives us would still have some uncertainty. And the uncertainty, a general rule we can use is that the uncertainty would be 5 in that next unwritten digit. So the 476 are all digits that the computer gave us. The next digit that the instrument didn't give us has an uncertainty of 5. So these are all the digits that the instrument gave us. The next digit has an uncertainty of 5. Another way of saying that might be half of the smallest digit that was provided. So half of 0.001, or maybe the better way of saying it is half of the smallest increment that the instrument can display. So this instrument can only go from 0.476 to 0.477. The smallest increment this instrument can display is 0.001 kilograms. So half of 0.001 kilograms would be our uncertainty. Okay, and that's with a perfect instrument. And what we're saying is, and I hope this makes sense. So imagine I've got 12.474 right here, 12.475 right here, 12.476 right here, 12.477 right here, and 12.478 right here as possible values. The computer told us, or the instrument told us, that it thought the answer was closest to 12.476. If it had been closer to 12.475, the instrument would have told us. If it had been closer to 12.477, the instrument would have told us. So there is a range of possible values that go from halfway between 12.475 to halfway and 12.476 to halfway between 12.476 and 12.477. That is the range of values that the answer could be. And by the way, it has an equal chance of being any of those values, right? Any one of those values would have rounded down to 12.476. If I think of this as like a probability, the probability that the answer is 12.474 is 0. The probability that it's 12.475 is 0. The probability that it's within this range is not 0, but it's equally probable for all those values, and then the probability outside that range is 0. And again, all that's for a perfect instrument. But there's no such thing as a perfect instrument. Every instrument has some inherent uncertainty to it. And what that means is, it is possible that if the real value was close to the edge, and it should have said 12.476, it might actually say 12.475. Because real instruments aren't perfect, and they can sometimes make mistakes. And so if I had a real instrument that's not a perfect instrument, there actually could be, a probability distribution that looks more like, it could be out here, but it's not very likely. It's more likely to be somewhere in the center. It could be here. Okay, something like that. And what that's saying is, it's possible for the machine to make a little bit of a mistake. Now, a higher quality machine, that curve might look more like, this, where it only can make a mistake if it's right near the edge. So real digital instruments might have a bigger uncertainty than half of the smallest increment. And if we have a digital instrument that was given to us, or that we purchased from a reputable, good company, then that's going to come with a owner's manual. And the owner's manual is going to tell us what the uncertainty is in the instrument. And usually these are written in a kind of weird way. The owner's manual will say something like plus or minus 0.1% plus 2, which is a weird way of writing uncertainty. And what does that mean? What it means is that there's an uncertainty of 0.1% of the measurement value plus 2 in the smallest digit. So if we measured 12.476 and we had this particular instruction in the instruction manual, we'd say, okay, well, my uncertainty is 0.1% of 12.476. So I'm going to type that in my calculator. 12.476 times 0.001, which is 0.1%. So that 0.1% is 0.01247 kilograms, and then the plus 2 means 2 in the smallest digit that the instrument can read, which would be 0.002 kilograms. So the total uncertainty is what we get when we add those things together. So we get 0.01476 kilograms as the sorry, that's not right. Oh, no, that is right. Sorry, that is right. Because I added, yeah, that's right. Okay, and so this would be the actual uncertainty from that imperfect instrument. And that you notice that the uncertainty is bigger than the 0.005, which is what the uncertainty would have been for a perfect instrument. Okay, that's digital instruments. What if we have an analog instrument? And the one I want us to think about is a clock. So clocks, an old-fashioned analog clock. So that's 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, 1 o'clock, 2 o'clock, 4 o'clock, 5 o'clock, 7 o'clock, 8 o'clock, 10 o'clock, 11 o'clock. So that's 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And let's imagine we have a perfect clock that knows exactly what time it is, and it's trying to tell us exactly what time it is. But let's also assume that this perfect clock we have only has an hour hand. So here's my hour hand. I say, okay, I've got a perfect clock, but there's an hour hand, and it's telling me that it is somewhere between 2 and 3 o'clock. Now, I might try to estimate and say, well, it's a little bit closer to the 2 than it is to the 3. I know if it was right in the middle, it would be 2:30, so maybe it's 2:20, right? But is it exactly 2:20? No. Even though the clock is perfect, I'm reading the clock. And when you're reading an analog instrument, you have to make an estimate. Even if the hour hand looks like it's exactly lined up with the 2, what if the hour hand looks like it's pointing straight at the 2? Does that mean it's exactly 2 o'clock? Well, no. Again, I have to estimate. It could be a few seconds after 2 o'clock. It could be a few minutes after 2 o'clock. And so we have to estimate. So let's go back to the situation where the hour hand is somewhere between 2 and 3. Okay, so there's my hour hand, and now it's even closer to the 2. So again, if I were to estimate, I'd be like, well, maybe that's about 2:15. But what's my uncertainty? And so it depends. It depends on the situation. In this case, I know that 2:30 would be halfway between 2 and 3. And maybe it looks like it's a little bit closer to 2:30 than 2 o'clock. So maybe I would guess it's 2:20. Or maybe I would guess it's 2:17. Or maybe I would guess it's 2:16. right? But I'm having to make an estimate. So there's going to be some uncertainty. Even if the clock is perfect, even if it puts the dial exactly where it's supposed to be, there's some imperfection in the process of reading. And like the digital instrument, the standard rule we use for interpreting an analog instrument is half of the smallest increment. And in this case, the smallest increment on the numbers is 1 hour, right? The smallest increment is 1 hour. The smallest marking on the instrument is 1 hour, so half of that would be plus or minus 30 minutes. So if I only had an hour hand, my clock, I could estimate the time, but I would usually say the plus or minus 30 minutes. And you might be thinking, whoa, plus or minus 30 minutes, that's a lot. I don't think it's really plus or minus 30 minutes. And I agree with you. Maybe it's really plus or minus 10 minutes. Maybe it's really plus or minus 5 minutes for this particular example. And that's because the 1 o'clock and the 3 o'clock are pretty far apart from each other, and we can really tell, is it halfway in between, or is it just a third of the way, or is it a quarter of the way, and we can make a pretty good estimate. But, for example, on a meter stick, the millimeter marks are really close to each other. And if we have an object and we're trying to measure how long it is, it's going to be harder to tell. Is it halfway between those two marks, or is it closer to this mark, or is it closer to that mark? And so the rule of thumb is that we use half of the smallest marking on our analog instrument. So what if we also had a minute hand? If we also had a minute hand, and the minute hand went to here, what we know is that for minutes, this is 5 minutes, this is 10 minutes, this is 15 minutes, and this is 20 minutes. So we're between 2:15 and 2:20, and so we might say, oh, it looks like 2:17 p.m., right? Because it's a little bit closer to the 15 than it is to the 20. So I might say, oh, yeah, that looks like about 2:17 p.m. But again, there's going to be an uncertainty. There's going to be a plus or minus. And what's the plus or minus? We usually use half of the smallest increment on the instrument. In this case, the smallest increment on the instrument is 5 minutes. And so if the smallest increment on the instrument is 5 minutes, then this would be plus or minus 2.5 minutes. Now, it would be different if this was a different clock and it actually had those little minute lines between the hour marks, then maybe we could be even more precise. Maybe we could be plus or minus half a minute. And if there's a second hand, then we could be even more precise. Maybe we could be plus or minus half a second. Okay? So hopefully you see how that works. All right. So if we have a digital instrument and it's perfect, the uncertainty is going to be about half of the smallest increment that the digital instrument can display. If the instrument is not perfect, then the uncertainty might be bigger than that. If we have an analog instrument and we're measuring it, usually the uncertainty is about half of the smallest increment on the analog instrument. And that's if the instrument is perfect and if the person using it is perfect. But sometimes the uncertainty is bigger than that. If I'm using a meter stick to measure the length of a rod, and I am able to put that rod on a table and to put the meter stick on the table right next to the rod, and I can look at these little millimeter marks, I might be able to measure this rod to within plus or minus half a millimeter, because half a millimeter is the smallest marking, or 1 millimeter is the smallest marking on the meter stick. But if there are a couple things that could make this harder. If the meter stick, for some reason, has to be further away from the rod, then it's harder to look and see exactly which millimeter line the top of the rod lines up to. And so then we might have more uncertainty in our measurement. And there's lots of other examples of why we might have more uncertainty than just half of the smallest marking. Okay, finally, because there's uncertainty when we're making a measurement, it is often the best practice to measure something many times, to make multiple independent measurements. So let's say I needed to measure the height of this rod. I can't put the ruler right next to the rod for some reason, so it's hard to figure out which millimeter line it lines up to. And because it's hard to know which millimeter line it lines up to, it's hard for me to know how big my uncertainty is. I'm not sure what my uncertainty is. Is it 2 millimeters? Is it 4 millimeters? I just don't know. So the best thing I can do is make multiple independent measurements. And what that means is I need to measure this several times so that each measurement is completely separate from the measurement before. So if I'm going to do that to measure this rod, I might use 5 different meter sticks, and also use 5 different people to read the meter stick, and also have those 5 different people not tell each other what they measured, so that they're not biasing them. And if we do that and we get 5 different values, and maybe the first person measures 347 millimeters, and the second person measures 349 millimeters, and the next person measures 351 millimeters, and the next person measures 348 millimeters, and the last person measures 346 millimeters. Okay, then we've got 5 independent measurements. And those 5 people now can share with each other what they got, and together they can try to determine what they think the length of the rod is. And so the best way to do this is to take the average of those 5 measurements. So in this case, 347 plus 349 plus 351 plus 348 plus 346 divided by 5. The average is 348.2 millimeters. So that's what, together as a group, we think the length of the rod is. So what's our uncertainty then? Well, it's not plus or minus half a millimeter, because we're not using that meter stick in its most perfect way. We're not getting the best possible measurement out of that meter stick. So if we want to figure out what the uncertainty is, what we want to do is find what's called the standard error. Of those 5 values. And there is a formula for doing that. which I don't expect you to memorize. And you can probably do it in your calculator. But again, I don't really expect you to memorize how to do that. I just use Google and type in standard error calculator and do this on a computer. So I'm going to type in the values, 347, 349, 351. Sorry, I'm wasting your time. I should have had this done prior to making the video. And 346. 1, 2, 3, 4, 5 numbers. 347, 349, 351, 348, and 346. All right, I'll calculate the standard error. What happened? Okay. Sorry. There we go. And it calculated the average for me and also got 348.2, so that's good. It calculated the standard deviation, which I don't need, and it calculated the standard error. And the standard error was 0.86 millimeters. And so that is the uncertainty in my measurement. Okay. All right, I want to talk really quickly about significant digits. You've definitely learned about this before in chemistry class. I want to talk about it again here. And the issue is, what if my calculator says 3.826, well, better yet, if I type in 4.7 divided by 8.3 into my calculator, it's going to give me 0.566 265 060 240 96. And of course, that's not the exact right value. There are more digits after that one. But those are the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Those are the first 14 digits of the answer. And those are the only 14 digits that my calculator can give me. And maybe your calculator doesn't even give you that many digits. But okay, we got 4.7 divided by 8.3, and this is what the calculator gives me. And the question is, well, what do I write down? And let's say that one student wrote down 0.57, and another student wrote down 0.566, and another student wrote down 0.563. What is the difference between those three answers? Okay, well, imagine it's like a perfect digital scale. 0.57 really means anywhere between 0.565 and 0.575. It means it's somewhere in the range between 0.565 and 0.575. And if you want to say 0.5749, that's fine. So it's somewhere between 0.5650 and 0.5749, because that's what that means, right? Because if I only write down two digits, it means I've rounded it to the closest two digits. So this is, okay. So this has an uncertainty of 0.005. If I write down 0.566, what I really mean is that it's somewhere between 0.5655 0.5 and 0.56649. What I'm really saying is that there's an uncertainty of 0.0005 in the value that I'm reporting. And if I say 0.5, this one, 0.56625, all the way up to 0.56639, which means, again, that there's an uncertainty of 0.00005. So when we write down a number with a certain number of significant digits, what we are saying is there is some uncertainty in my answer. And if I write down all the digits, that means that I think my answer has an uncertainty of 0.0000000000000 whatever. And if, by the way, if this answer is supposed to be kilograms, you're saying that your answer has an uncertainty of, less than the mass of a, less than the mass of a cell, I'll say, the cell of a human body. And by the way, you probably didn't measure it that accurately. So significant digits is kind of I'll say, sloppy way of telling what the uncertainty is in the number you're writing down. And the uncertainty is 5 in that next unwritten digit. Plus or minus 5 in the digit you didn't write down. So the reason your chemistry professors were very picky about significant digits is they wanted you to be reporting the correct uncertainty in your answer because the values we were given had some uncertainty. That 4.7 had an uncertainty of plus or minus 0.05. And the 8.3 had an uncertainty of plus or minus 0.05. So our answer really ought to also have an uncertainty of plus or minus 0.05, which is why your chemistry professor would have told you to write the answer as 0.57 kilograms in this case. Okay, but I'm a physics professor, not a chemistry professor, and I'm actually even more picky. When we're doing labs, I don't want us to just use significant figures to determine our uncertainty. I want us to actually write down the real uncertainty, in this case, 0.86. And actually, what the computer told me, the standard error from the computer was actually not 0.86. The standard error from the computer was 0.8602325267, but I'll just write down a few extra digits, 233. So the computer calculated the standard error, and of course it got this number. Okay, so last thing in this video, and this is a very long video. If you watched this whole thing, I feel sorry for you. Last thing I want to talk about is how do we report uncertainty? How do we report uncertainty? And one way to do that is with significant digits, right? If you know that your uncertainty is 0.005, sorry. What I said before was a little confusing. In chemistry, there are 2 digits here, so there are 2 digits in our answer. It actually has very little to do with the 0.05. It just has to do with 2 digits. I can talk about why if you're curious, but I did say that wrong a little bit earlier. Anyway, we're reporting uncertainty. Let's say we want to actually report our uncertainty. So we have measured something. Maybe we measured a time and we got 859,435.8 seconds, but we know because of how we did our measurement that there's actually an uncertainty of 1,347.9 seconds. And you might ask yourself, well, how would you know that? Well, maybe we measured it 10 times and we took the standard error, and this was our standard error. So we've got this value. This is the answer. We call this the value. And we've got an uncertainty. And we want to now report this, and we want to write down our value and our uncertainty. And we want to do it in a correct format. Okay, so the first thing we need to know is that our uncertainties are always estimates. We are estimating our uncertainty. Now, this might be the exact standard error, but standard error isn't uncertainty. Standard error is an approximation of our uncertainty. It's an estimate of our uncertainty. So we are always just estimating the uncertainty, so it doesn't make any sense to have 5 significant digits in our uncertainty. In fact, our uncertainties will always have either 1 digit or 2 digits. Okay, so how do we decide? What we do is we look at the first 3 non-zero numbers. In this case, they would be 135, because we would round that to 135. And then we look in a table. And if those first 3 numbers are between 100 and 354, then we're going to keep 2 digits. If they are between 355 and 949, we're going to keep 1 digit. And if it's between 950 and 999, we're going to keep 2 digits. And in this case, the 2 digits will keep, because if I round that to 2 digits, I will get 1, 0. So the 2 digits I'm going to keep are always a 1 and a 0 in that last case. We'll see how that works in just a second. Okay, so in this case, I look at the first 3 numbers, and that rounds to 135. So 135 is in this range, which means I want to keep 2 digits. So if I keep 2 digits on 1,347.9, that becomes 1,300. So my plus or minus is going to be 1,300, because I kept 2 digits, because the first 3 digits in this uncertainty were 135. I know it's 134.7, but that rounds to 135, and 135 is in the range between 100 and 135, and so we keep 2 digits. The 2 digits are the 1 and the 3, so 1,300. Okay, now, the next thing I want to do is write down the value. And here, I'm not counting the number of digits, I'm looking at which digit to keep. And the most precise digit in my uncertainty is this 3. Because the 1 is in the thousands place, and the 3 is in the 100s place. So I want to keep the most precise digit. I want to keep the 100s place, which means I also want to keep the 100s place in my value. So that's going to be 859,400. And the reason I do that is because I know that 3 is an important number, I want to keep the number that I would be adding or subtracting it to. So when I add or subtract 1,300, I want to be able to add or subtract to the 100th place. So I'm keeping that 100th place. And of course, this is seconds. And we keep the seconds outside of the parentheses. We put the value plus or minus the uncertainty inside the parentheses. We keep the units outside the parentheses, and that means that seconds goes with both the value and the uncertainty. Okay, let's look at another example. Let's say we measured a distance and we got 0.062 meters as our value, and our uncertainty was 0.0005551 meters. And we want to write this down correctly. So again, the first thing I want to do is figure out how many digits I should keep in my uncertainty. And we're always either going to keep 1 digit or 2 digits in our uncertainty. So is this 0.0006 or is it 0.00056? How many digits should I keep? Well, what I'm going to do is look at these first 3 numbers. 555. That is in this range. It's between 355 and 949. So that means I want to keep 1 digit. So that means my plus or minus is going to be 0.0006. So I round to the nearest 1 digit. Okay? And that digit is in the tenths, 100ths, 1000ths, 10,000ths place. That digit is in the 4th digit after the decimal, which means I also want to keep 4 digits, 1, 2, 3, 4 digits after the decimal in the value. So I'm going to be rounding this to 0.0628 meters. Okay? So because this was in the 1,000th place, we're also keeping the 1,000th place in our value. And so we've got our value, 0.0628, plus or minus our uncertainty, 0.0006 meters. And this is the correct way of reporting this measurement. All right, let's do one more example. Let's say we were measuring the mass of a planet, and we got 8.91532 times 10 to the 24th kilograms for the value, and 0.98632 times 10 to the 21st kilograms for the uncertainty. Now, the first thing I absolutely have to do is get these times 10 to the same. I have to put them in the same times 10 to the. So I've got to convert one of these. I'm going to go ahead and convert the value to have times 10 to the 21st. So if I want to keep this thing the same, if this goes from 10 to the 24th to 10 to the 21st, that means I've divided by 1,000. So I need to also multiply by 1,000 so that the result stays the same, right? If I divide it by 1,000 and multiply it by 1,000, then I haven't changed the answer. So if I go from 10 to the 24th to 10 to the 21st, I've divided by 1,000, which means I have to also multiply by 1,000. So this becomes 8,915.32 times 10 to the 21 kilograms. So this number and this number are the exact same number. Okay, plus or minus 0.98632 times 10 to the 24th. Times 10 to the 21st, sorry. Kilograms. Okay, so now I can go through my process. I look at the first 3 digits, 986. 986 is between 950 and 999. So I want to round to 2 digits. So when I round this to 2 digits, okay. So how do I say this? So we're going to round up to 1, but we're going to keep 2 digits. So if I'm looking at this number, if I'm rounding up to 1, that I'm going to round up to 1, but I'm also going to keep 2 digits, 1.0 kilograms. Right? Because if I tried to keep, it could be 0.99, but that's not what I'm supposed to do. I'm supposed to round to 1.0. Okay. So 1.0, and then okay, and except I still need my times 10 to the 21. That didn't go away. Times 10 to the 21 kilograms. So now I want to round this to the same place. So it's the tenths place. So I'm going to keep the 0.3. So this is 8,915.3 times 10 to the 21 kilograms. And now, when I'm writing this, I take the times 10 to the 21 kilograms out of the parentheses, and I just leave the values 8,915.3 plus or minus 1.0 times 10 to the 21 kilograms. And that's the best way to write that. Okay, this was a lot. I don't recommend watching the whole video over and over again. I will try to put something in the comments where I can tell you where to jump to in the video to see different parts of the video. And I hope you have a good day.